Okay, so welcome to the second of these video tutorials on momentum. This video tutorial is going to be talking about momentum and its conservation. So first off, we're going to ask ourselves the question is, what does conservation mean? And in regards to momentum, what it means is the total amount of momentum in a closed system will always remain constant. Okay, so let's talk about what this term closed system means. And it basically implies that there's no outside forces. Okay, so when we say that there's a closed system, we're looking at just an interaction between two objects. So they apply a force on each other, but if I look at the system as a whole, there's nothing else influencing it. Meaning like the two colliding carts, like we did in class, well, there was no friction to account for to slow the object down. So what this comes out to, and you see this in your reference tables, is the total momentum of all the objects, two or more, before a collision, is equal to the total momentum after a collision. So if I sum the momenta before and I sum the momenta after, those two are equal. And remember, too, that momentum is a vector, so we have to account for the directionality to it. So mathematically, this works out to be the momentum of the first object plus the momentum of the second object equals, and this could be, you could have a string of 3, 4, 5, or 6 objects. We'll deal with 2. Is equal to the momentum of the first object after, so we'll use the prime notation for that, plus the momentum of the second object after. So that's the general equation that will apply for all of our different types of collisions. Speaking of different types of collisions, the first one that we'll be talking about is an elastic collision. And when two objects collide and separate without any sticking. Meaning that they pop apart and they are not still physically interacting with the other object. So you can consider two billiard balls. So a billiard ball with mass m comes in with speed v. It collides another object with mass m that is stationary. And then after, the ball that came in is now at rest, and the ball that was at rest is now moving with the exact same speed v. And you can see this with if you play pool. When the cue ball comes in and hits one of the other balls, it might come in with some speed, stop, and then that ball goes off with the exact same speed. And that's actually very close to a true elastic collision. And so what we can conclude from this is that when they have the same mass, so when the two objects have the same mass, they trade momentum. Which also means that they trade velocity. Because if they have the same mass, then in order to keep the same momentum, then they must have the same velocity. So an example of this is a 2 kilogram ball moving at 3 meters per second collides with a 3 kilogram ball at rest. So we have a 2 kilogram ball going at positive 3 meters per second. So our before picture looks something like this. That's at rest. And the assumption is that after, the 2 kilogram ball is not moving, and the 3 kilogram ball is going off at some speed. And we're asked to find how fast is it moving after. So I can write my conservation momentum equation and cross off some things that are 0. So before, the 3 kilogram object wasn't moving. And then after, the 2 kilogram object stops. So our equation simplifies pretty quickly here. And so we have the 2 kilograms before, times the positive 3 meters per second before equals the 3 kilograms after times my unknown V2 prime. When you plug that in, you get V2 prime to be a positive, meaning it's going in the same direction that the 2 kilogram ball was originally going, 2 meters per second. An inelastic collision is when two objects collide and they stick together. And so we can have a situation, a ball of mass m moving at some speed v collides with a stationary ball, also mass m, that was initially at rest. And then after the two objects, think of their, Velcroed, there's Velcro between the two of them, go off and move at some speed that we don't know. However, what we could say is that since there's twice the mass, there's going to actually end up being half the velocity. And we'll see that work out in the mathematics of it. So the masses of the two objects, they combine to form a single mass. So let's try that out in a problem. We have a 5 kilogram ball moving at 6 meters per second collides with a 10 kilogram ball moving at minus 6 meters per second. So if the two carts stick together during the collision, what is their final velocity? So we have a 5 kilogram cart moving at positive 6 meters per second. And we have a 10 kilogram cart moving in the opposite direction at minus 6 meters per second. So if I write out my conservation of momentum equation, plus m2 v2 equals m1 v1 prime, what I have here is on the right-hand side of this equation, v1 prime and v2 prime, because they collide and stick together, they move as one. I can write that as just v prime. So I have m1 v prime plus m2 v prime. And since they are the same v prime, what I can do is I can pull that out, factor that out of my expression. And that's the trick of the mathematics in order to solve this. So I have the same left-hand side. So I have 5 kilograms times a positive 6 meters per second, m1 v1, plus m2 v2, 10 kilograms times minus 6 meters per second. That is equal to my unknown, which I'm asked to find, times my m1 plus m2. So that's 5 kilograms plus 10 kilograms. So if you go through and solve this, what you end up getting, you have positive 30 minus 60 equals v1 times 15. Okay, and then minus 30 equals v prime times 15. Divide by 15. And we get v prime equal to minus 2 meters per second. And this does make conceptual sense if you go back up to the original scenario. The cart that was moving to the left had more mass, and they're going the same speed in opposite directions, so it has more momentum. So when they collide and stick, they're going to be moving together to the left. All right, and then the last scenario is an explosion, a popping apart, and a separation. But basically, is that two objects that are being held together. Think of a spring, a magnet, or something along those lines. So two objects held together, they get pushed apart. So mass m connected to another spring, which is next to another mass m. They're initially both at rest, so they have zero momentum before, so they must have zero momentum after. And the only way that that can happen is that if one goes in, let's say, the negative direction, and the other one goes in the positive direction, and if the one that's going in the negative direction works out to be, let's say, negative 10, and the one that works out to go in the positive direction would be positive 10. So negative 10 plus positive 10, we get 0 after. This doesn't have to be the case, but as we will see it, is that we will see that these usually start off with a momentum 0. So they will usually begin with a momentum of 0. So an example of this type of problem is we have a 100 kilogram cannon with a 5 kilogram cannonball. So we have some cannon and it's firing some cannonball. And so we have 100 kilograms, and then the cannonball is 5 kilograms, and it's just about to be fired. So what we know that the after effect of it is the cannon is going to be moving in one direction, the cannonball is going to be moving in another direction, the 105. So if I set up the M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime, the whole left-hand side of this equation is 0. So I have 0 equaling, let's call M1 our cannon, 100 kilograms times V1 prime plus 5 kilograms times V2 prime. Okay? And so this is actually what we're asking down here. And the first part of this is when the cannonball is fired, what happens to the cannon? It gets shot backwards. So this is what we call a recoil. So the cannon, as we suggested, is going to be moving towards the left in our diagram. If I wanted to know the velocity of the cannon, then, and I'm given the velocity of the cannonball is moving at this V2 prime at 20 meters per second, then what we have here is 0 equaling 100 V1 prime plus 100 kilogram meters per second. So if I subtract the 100 over, equaling 100 V1 prime, and divide by 100, I get V1 prime equal to minus 1 meter per second. Okay, so that's all for now. We'll talk more about this in class tomorrow. I hope you enjoyed, and thanks for watching. Have a good night. Bye-bye.